welcome back. So we are going to continue from where we left. We are going to deeper into the discussion of differential amplifier, fully differential amplifier. We are going to look into transistor level implementation of such a fully differential amplifier and look at the basic analysis starting from DC biasing, then going towards the frequency response, stability analysis, noise analysis, and so on, so that we can figure out how to achieve a given set of matrices. So we have seen at the topmost level we have arrived at some design specification for the front-end amplifier that translates to transistor level specifications. So first we will try to see how to choose a particular topology and go for the transistor level design, and from there how to do the analysis for those particular specifications. So let us get started with a simple fully differential amplifier using MOSFET transistors. So this is a single stage fully differential amplifier, provided you have a bias point over here, Vp, you call this M1, M2, M3, M4 and M5, and we are assuming that Vp has been provided by some appropriate biasing scheme, and we will be discussing that very soon. And here, if we revisit our concepts of differential amplifier operation for a fully differential signal, we know that we can call this V1, V2, and the differential component of the signal can be identified as V1 minus V2 by 2, and for the differential half circuit I can represent the differential half circuit as this by putting an AC ground at the source of M1, and M3 gate also becomes AC ground because it is a DC bias point, and you are having the V differential applied over here. What is V differential? That is Vd is V1 minus V2 by 2. So you have Vd applied over here, and we know that for this particular signal our output signal VO1 will be given by Vd times minus GM times the output resistance over here, small signal output resistance over here, which is RO1 parallel RO3. So this breaks down to a simple common source amplifier with an active load. And looking from the basics, we understand what is the need of an active load. The main advantage of an active load is that it can give us large gain without compromising upon the DC bias point. So if we want large gain with a passive load, what is the criteria? If you are looking for a common source amplifier with a resistive load or a differential amplifier with a resistive load, in order to increase the gain, there are two options: either you increase the bias current or you increase the RD. And larger and larger value of RD means larger and larger area, because passive resistance takes large amount of area. So using a passive resistance also you can get large gain. For example, the two options that I have here for achieving a larger gain is GM and RD. So if I go for increase in RD for a given bias current, we know that the DC bias point over here given by VDD minus ID RD will be coming down. So if I am fixing my bias current to ID and trying to increase the gain by increasing RD, then I know that the DC bias point over here will be going down and down. And I know that for a symmetric swing or maximum possible swing, I should bias this DC point at the output close to the midpoint of maximum and minimum allowed voltages. So in a circuit, if you are finding out what is the maximum allowed voltage over here at this node to keep the transistors in saturation, and correspondingly what is the minimum allowed voltage, that gives you the range of the signal swing that you can have at this point, and a good DC bias point would be the midpoint of that. So if I am just going on increasing RD in a passive load resistive load amplifier, the DC point will be going down. Therefore, in order to maintain the same DC point, the only option is that if I am increasing RD, I must also reduce ID by the same amount, so that the DC bias point remains close to the desired value. So if I am increasing RD, I must reduce ID by the same factor, so that my DC bias point is not disturbed. It is same as the previous desired value. In that case, I know that GM is proportional to root ID. So if I am increasing RD by a factor of k and reducing ID by the same factor, the GM RD product is going to go up by root k. That means you will be able to increase the overall gain by root k by increasing the RD and reducing ID by the same amount while keeping the DC bias point intact. So even with the passive load, you can get large gain, and you have similar trade-offs with other important quantity, which is the bandwidth. So just like you're increasing the RD, ultimately the RC time constant at this point will become larger and larger, and in order to calculate bandwidth, you can look at the R equivalent at this node. If the RD is increasing, the R equivalent at this node also goes up. As a result, your bandwidth is also going to come down. So you do have the similar constraints, similar trade-offs, trying to increase the gain by increasing RD. You are reducing the bandwidth. But the other important factor is the area. So the area of the resistor increases proportionally with the value, and as a result, you will end up consuming a huge amount of area if you are trying to go for larger passive resistance. So in order to avoid that, we can rather opt for active loads where you can get very large value of small signal resistance provided by these MOSFETs by controlling some parameters like the bias current or the channel length. So we know that the small signal resistance of the MOSFETs is given by 1 upon lambda ID. Lambda itself is going to reduce if I am increasing the channel length. So I can write this as lambda dash L upon ID. So if you are having larger and larger channel length, we know that from the device, the effective delta L produced by the channel length modulation, the delta L by L factor will be smaller if you have larger L. As a result, a larger channel length will ensure a larger RO and a smaller lambda. So lambda can be written as lambda dash upon L, where lambda dash is independent of L. So in order to increase RO, or the small signal resistance for the MOSFET, I have two options. I can reduce the ID or I can increase the L. Increasing the L does not drastically increase the area of the MOSFET because L consumes relatively smaller footprint in the entire MOSFET. So if I am looking at the top view of the MOSFET, this is the source, this is the drain. These small squares are the contacts that you make with the source and drain regions, and then you have the gate contact that you make with the polysilicon gate. So the gate generally does not consume so much area. The channel length does not consume so much area. So by increasing this dimension, you are not sacrificing too much of area. And the other strong option that I have for increasing the gain is the ID. I can lower the bias current in the circuit to achieve larger gain. So there I can use active load, I can employ smaller and smaller bias current and longer channel lengths to have a large RO and at the same time get large gain without sacrificing the area significantly. As you will see that, of course, reducing the bias current can trade off with other important specifications. One of them, of course, is the bandwidth, and the other one being noise. As we go towards small signal analysis, frequency response, and noise analysis, we will see that the bias current plays an important role in determining noise, and hence we cannot arbitrarily lower the ID to increase RO. So that is one of the main reasons why we are using the differential amplifier with active load. Now let us ask the question regarding the DC bias point. We know that for a passive load common source amplifier or a passive load differential amplifier, the DC bias point at the output is well defined, because if you are biasing the differential amplifier with a current ID, bias current ID, and you have resistive load over here, both of them RD, I know that the DC bias point is going to be VDD minus ID. So if I am replacing this by RD, the DC bias point is VDD minus ID by 2 times RD if ID is the total bias current of the tail current source. And RD is a passive component and it can also vary, it may not be very precise. In integrated circuit design, using proper layout techniques, we can ensure that the two RDs, the passive RD on the two drains, they are very close together. We can match two RDs, as we will see in subsequent sessions. We can match two RD values very closely within 0.1%, but the absolute values can vary a lot, maybe even 10%. But still, 10% is within limit. So if you're trying to bias this with say 0.5 volt, it may end up being 0.55 volt or 4 or 5 volts, still worst case it will be tolerable. So we have to keep that much margin, but still it is relatively well defined. There are ways in which we can define the current source also pretty precisely, and we can have very well controlled current source. You can have a current reference, as we will see in the course. We can design very precise current references to appropriate techniques, and we can have a very well defined current source. Once you have a precise current reference located somewhere in the chip, you can copy that current reference using current mirrors at different points. If you want more accuracy, you can use cascade current sources and have more accurate control on the current source. So current is a value that you can have much better control. You can precisely control that current value, because when you are forming current mirrors, there also one side is having the reference current. The transistors which are forming the mirrors, they also can be matched. Two NMOS transistors or two PMOS transistors can be matched very well by appropriate layout techniques, and therefore you can have current defined in a very accurate fashion. So if you are having current defined in an accurate fashion, then for a resistive load, only the variations in absolute value of RD becomes the limiting factor on the DC bias point. But if the technology is good and the absolute variation in RD is within, say, plus minus 10%, then you still have good control on the DC bias point. Whereas if you go for the active load, there you know that the output DC bias point is primarily determined by the channel length modulation factors, because here what you are trying to do, you are trying to establish a DC current in M1 with the help of the tail current source. The gate voltage of M1 is also fixed, gate voltage of M3 is also fixed, and therefore the output DC point is going to be determined only by the source to drain voltages, because the drain current you are enforcing a certain value, gate voltages you are enforcing a certain value, and therefore you are left with the VDS to determine the output DC point, and the VDS in turn depends upon the channel length modulation factor. So even if you look at this simple example of a common source amplifier with active load, in order to determine the output DC point, we will equate IDN to IDP, and in this case we know that Kn times the VGS, where the VGN minus VTN square should be equal to the Kp times the VSG, where Vs is VDD minus mod VTP minus VGP square. Now here if we look at these quantities, the VGN is fixed, VGP is fixed, because the biasing point of the gate voltage of M3 and M1, they are being determined by the circuits. So you are already biasing M3 and M1 gates appropriately, so the VGN, VGP become fixed. VT and VTP can vary from device to device significantly, Kn and Kp can also vary, and then you have the channel modulation factor 1 plus lambda n times the Vd. If I assume this is the common source amplifier, this source ground, then we have the Vd directly coming over here, and in the PMOS equation I will have VSD. So VSD is basically VDD minus VSD, and therefore we can see that if you want to solve for VSD, ultimately is going to be determined by the ratio of Kn Kp, ratio of the lambda n and lambda p times 1 plus lambda VSD. So I have to 1 plus lambda p times VSD. So here you will be finding out the expression for Vd, which is going to be determined by the lambda p lambda n ratio and also the Kn Kp ratio, and all these values, the Kn Kp ratio, that is the transconductance parameters of NMOS, PMOS, and the lambda n lambda p ratios can vary a lot from device to device, and therefore we don't have much control on the output DC point over here. And therefore one of the main limitations of the active load device is that we need to make sure by appropriate biasing scheme that the output DC point is well defined, and for that we will take help of common mode feedback that we'll be studying in the next session. Apart from the output DC point, we also need to look at the frequency response considerations. So with respect to frequency response, as we said, the limitation as compared to the passive load can be similar. So as you are trying to increase the gain, as we said, we have the two parameters I, D and L. So once again, reducing the ID or increasing the L, both of them are going to have negative implications on the bandwidth and hence frequency response. So that concern remains as it is. So apart from the DC bias point, if we consider some other aspects related to the circuit, we will see later that with respect to some very important parameters like common mode rejection ratio or power supply rejection ratio, also the choice of PMOS device or PMOS active device can play an important role. So in our earlier specifications, we have not discussed two very important characteristics of differential front ends, that is the common mode rejection ratio and power supply rejection ratio. So we will visit these a little later in the discussion. We know that common mode rejection ratio for a differential amplifier is the gain of the ratio of differential gain and common mode gain, and a good differential amplifier should have a very high common mode rejection ratio. We have also seen that we are using a fully differential topology, and for a fully differential topology, as long as the signal is remaining differential all throughout the chain, CMRR ideally it may not play an important role, but there are other constraints, there are other considerations related to mismatch that will also degrade CMRR even for a fully differential topology. So we'll see that in case of fully differential amplifier, the CMRR is mainly degraded because of mismatches. So this will require separate discussion. Another important factor is PSRR, power supply rejection ratio. That basically determined by the ratio of the signal gain divided by the gain from power supply noise to the output. So we say this is the differential gain upon, or let me write it as differential gain AD upon A VDD. That means if you imagine that the power supply itself is having some noise over here, and how does that power supply noise translate to the output of the amplifier? So that gain is going to be defined as AVDD. So and for a good differential operation, for a clean amplifier operation, I would like my AVDD to be very small. Even if the power supply is having some noise, it should not directly translate to the output of the amplifier. So once again, the choice of load can have significant impact on the power supply noise also, and we need to take into consideration PSRR. So we will see in subsequent discussion that these two parameters, CMRR, PSRR, also determined by the load conditions, or they are influenced by the load conditions, and we will try to arrive at the expression for PSRR and try to see how the load, the choice of load and the appropriate biasing topologies play a role in determining these two. So let us continue our discussion on the biasing scheme and the common mode rejection ratio and the common mode feedback in the subsequent session. So we stop here before we start the next module.